Woo! Ladies and gentlemen, this is the second to the last day that I will ever talk to you as far as statistics go, because after that, then you have to prove to me on Monday that you know how to do what I told you.
If we do this whole thing, can we
Yes. Yeah.
the whole thing?
Yeah, if you complete the whole thing, you don't have to.
Done already.
Just kidding.
What?
That
was.
So, the answer key, if you need the answer key, email me and I will email you the answer key. Okay? Sound good?
When is it?
That is not due. But
Study guides?
I am not. I'm not going to class.
Bro.
I'll put it in.
Here's my rewatch. Sir, can I get a review?
You? You too? Dude, that's a great band, you two. Ouch, you need one too?
Yeah.
Oh, I'm sorry. Okay, let's finish up what we got. Ready, set, I am going. So I have one problem, some notes with an example, and then one more problem, then I'm done for the day. Sound good? And then I have to go talk to a science class in a little bit towards the end of the period. Sweet. All right. This is problem number 3 of the 8.3 worksheet. So problem number 3, from the 8.3 worksheet, the hypothesis test for one mean. Okay, it has been known that the average age of a child gets his or her first ear infection is 22 months. Dr. Rollins believes that this data is wrong because he used a sample of 20 kids and found that the average age of the first ear infection was to be 27 months with a standard deviation of 3.1. Does this indicate that the average age of a child gets their first ear infection is older than the first thought? Use an alpha of 0.05. Okay? Everyone understand the problem?
Backpacks.
Backpack.
Backpacks.
So, okay, so we're going to do our hypothesis, which is average age of ear infection is equal to 22 months. Our alternative is average age is more than 22 months. So our alternative hypothesis should point to if this is a one or two tail test. Any thoughts? One tail. Okay? Because we want greater than. Okay? So we're looking at this kind of scenario. Okay? It's a one-tail test. We are going to use a t-score versus a z-score. The main reason that sticks out up there, well, there's two reasons, but the second one's not as important. Being we're only using 20 people, that's kind of a reason why we're going to point to using a t-test. But what's the main reason we're going to do the t-test? You don't have the standard deviation of the entire population, so I think you were onto the right track. So, being I do not have the standard deviation of these people, this should be pointing to the fact that we are using a t-test. The less than 30 is kind of, but it's not vitally important. Okay? All right, so what is the t-score? So if we find our t-score, we're going to take what we witnessed, or the doctor witnessed, over what the overall population was, over the standard deviation of our sample, over the 20 kids, and then if we found this, we came out to 7.21. So basically, this looks like this. is what we're looking at. Okay, so the t-score is mimicking the standard deviation. So this is kind of showing that we're like 7 standard deviations outside of what's happening here. Once we find that, we're going to look for our p-value. So t was here, then we look for the p-value. And the p-value, we're going to use TCDF on the calculator, 7.21, comma 1,000, comma 19. Okay, the 7.21 is our minimum value. We're going all the way up to 1,000. It could be 100. It doesn't have to be that high. But where did the 19 come from? N minus 1. And that's known as the what? Degrees of freedom. Cool. So if you do this on the calculator, we're going to come up with 3.79 times 10 to the negative 7. So that's 1, 2, 3, 4, 5, 6, 7, like that. Okay? We had said we're testing an alpha value of 0.05. So this is less than 0.05. So what do we reject? Null. Hey. So it points to that this doctor might actually be onto something. Okay? Hey, could average ages of ear infections and things like that change? Like this is pointing that it could. But are there things that might make ear infections change a little bit? Yeah, I mean, medicine's changing a lot, isn't it? There's no telling what you guys will see in your lifetime. In my lifetime, I remember the first artificial heart was successfully transplanted, and it's really, the first heart transplant of a real heart happened earlier than I was alive, but then they came up with an artificial heart. It was this plastic apparatus that had valves that opened and closed and had a battery pack along with it. And the patient, this is going to sound crazy, the patient did not live that long after. It was, lived like 20 days with an artificial heart. But, and people are like, oh, what's the big deal? Well, that was the first attempt, so they might be onto something. So medicine is changing. So this doctor to say, the average age of 22 months might not be, real. They've noticed a trend with his patient that things would happen. So there could be things going on with medicine that are preventing those ear infections from happening. You guys all know that ear infections, probably after you've had one, aren't the most fun. Okay, we will reject the null. Our conclusion that the average age of a child with an ear infection is greater than 22 months. We already said that. This could be a type 1 error, meaning that we selected of these 20 people that we selected, we just got lucky. Perhaps it was a sample that came from a different region, came from a different time of the year. It just didn't fit in. So it might have been a type 1 error where the average age of a child with an ear infection is over 22 months, but it really, truly was 22 months. So it's just kind of saying that type 1 error, that this might have been just a lucky pick, the right selection of kids to show that they had higher, but they really don't have that. So that's type 1. Okay. God bless you. All right, so on 8.4, which we're getting into, 8.4, I'm not going to have us do the activity, even though I saw a jump rope in class. And it says, and I'm not going to have you guys do this, so don't worry. But if you were to take your heart rate right now as you're sitting there, and then if you were to do 25 jumping jacks, would you think you would have a faster heartbeat? I mean, that seems like a thing. And again, I'm not going to do the experiment, but I know you guys don't really want to do jumping jacks at this point in time. But if I was evaluating everybody, or like this class, if I took a resting heart rate, then made us do some exercise and had an increased heart rate, being I'm testing the same heart but just in different conditions, I would then have to subtract my original from my findings. Okay? And it is possible that if you subtract one from the other that you could get negative numbers, and that's okay. Does that make sense? So the big equation that we're going to use is we're going to use this. Okay, so you notice that you have a mean difference and you have a standard deviation difference. So this means that we are going to take our data, we are going to use the one variable statistics and plug things in. So this particular problem for the example says a psychiatrist, or psychologist, wants to study whether sleep deprivation impairs memory. 10 subjects are obtained for use in the study. They are measured on the memory exercise where each subject needs to remember a certain number of words read to them, both after normal night of sleep and after a night of where they obtained no sleep. The results were shown in the table. So you have subjects 1 through 10, and then you have how many words that they could do with sleep, and then how many words they could do without sleep. And so what you're going to do is for each subject you're talking about, subject number 1, if I subtract 13 minus 11, I get 2. And then if I subtract subject number 2, that's going to give me 6, and I do number 3, I'm going to get 11 minus 12, so that's negative 1, etc. So if you were to go on the list where it was sleep and without sleep, and you were to go 13 minus 11, 15 minus 9, 11 minus 12, 8 minus 7, 16 minus 3, 15 minus 12, 17 minus 16, 13 minus 15, and 9 minus 8, you would get a difference. Does that make sense? So what you're going to do is you're going to take that difference, and I'm not going to plug the whole thing in, but someone have their calculator. Can I borrow your calculator? So all I'm going to do is I'm going to plug this in. I'm going to go stat, edit, and I'm going to plug in the differences. So I get 2, 6, 1, 1, 3, 3, 1, 2, 1, and 0. Stat, calculate, statistics. Sweet. So if you do the one variable statistics, you're going to find that you're going to get a new average of 1.4. Okay? And then you have the sample standard deviation, which is 2.27. Okay? You get that by plugging it into your stats in your calculator, finding the one variable statistics, using SX as our sample standard deviation. Okay? And then we're going to use an alpha value. So this is what we observed up here. We have an alpha value that we're going to use as 0.05. And then, let's see. Is it random sampling? It just says 10 subjects are obtained. I'm not sure if it's a random sample. It didn't tell us. Okay? Independence could be, is it normal? Well, being that you're talking about 10 subjects you're using, I'd say it's not going to form that normal curve as nicely. Okay? State the hypothesis. So our null is sleep deprivation does not impair memory. And our alternative hypothesis is sleep deprivation does impair. One or two tail. Why is it 2? Yeah. So it's at, having our hypothesis, we just want to know, does it impair a person's sleep? So we're looking at that scenario. Okay, might have a positive effect, might have a negative effect. We're going to do this the exact same as we would once we get our, my p-value, I'm going to double it. because the p-value is going to be the area on either side. It's going to be the same size area, so we can go ahead and compare it that way. All right, let's go here. So, plugging in our information that we have. So, to find our t-value, we're going to go x bar d. So, x bar difference is 1.4. What is that difference? So let me fill in the rest of this before I go and tell you how to do it. Okay? What is the mean of the entire population? Is it there or not? Do we have a mean of our entire population given to us in the problem? So this is unknown. We don't know what this is. So if we don't know what something is, what number should be plugged in for that? 0. Okay? So being this is not told to us, we have to call it 0. We're not going to count it for anything. So then this problem can be worked out as this, 1.4 divided by 2.27 divided by square root of 10. Work this out, you're going to wind up with, I can't see my stuff, 1.95. Okay? So then I'm going to do my TCDF. So I'm going to take this value, and I could have had this as the minimum or the maximum. It doesn't matter. So being I'm doing it this way, it's going to find me this area. But these two areas are equal in size. So if I did it this way, I should get the same results if I had 1,000, negative 1.95, or negative 1,000, negative 1.95, comma 9. Where did the 9 come from? 10 minus 1 is known as the what? Degrees of freedom. So you do. So did you get this originally? Roughly? And if so, that should come out to, so if I multiply that times 2, I get that. And is that value this value less than 0.05? It isn't. It's close. It's, I mean, you're talking about, 5 versus 8. But is this true or false? So that's a false statement. So we can reject this, or the terminology used is, so this starts to point to this, that we accept our null. Sleep depression does not improve memory. Wow. Cool. Can I move on? Last problem for the day. Y'all ready for this? Okay, problem number 1. For right-handed people, are their right legs stronger than their left legs? Several people who are right-handed measure the strength, or several people who are right-handed measure the strength of legs. The results are as follows. Determine if right-handed people do have stronger right legs. Okay. One thing that they didn't give you on this particular problem is they didn't give us alpha, so I'm just going to call alpha we'll make up alpha be a 0.10. Is that okay? Okay, so I'm making this up. It's not part of the problem. They had just forgotten to write it in there, so I'm just picking an arbitrary value. Is that okay? Okay, so being you're talking about the same person, you have right leg strength, left leg strength, and if you go through and you do the difference, so you go 10.2 minus 9.8, 11.5 minus 10.5 all the way through, you're going to be able to find the difference. Okay, so let's first off do our hypothesis. Right-handed. Don't as stronger. Right leg. And our alternative, we'd probably say okay, so we're just looking at strength. So I think we're going to look like this scenario. So I'd say it's going to be one tail. And then if you were to do all that difference, if you were to go through all this stuff, you're going to find that x bar is equal to 0.613. Your standard deviation of your sample is this. We're talking about 15 subjects that we're looking at. So if you go through, plug it in. So we're going to come up with that. Okay. Again, I used 0 because I didn't know what the entire population study had shown. We're starting a study because we made some observations. And then if I do TCDF, it's one tail scenario, 3.304 thousand and 14 as my degrees of freedom. And we're going to find out this is 0.00261. This is indeed less than the 0.1 that we had said. So we reject our null, which points to this taking place. I guess you could have a type 1 error where of our people that we sampled, maybe they don't have any different strength. It's just the people we found fell into that category. That's my second to last lecture for you guys. Is that all right? No applause, just for money this time. Woo!